So title of the talk is Fixing Big Data Engineering with SQL. The parentheses around the big is actually because what is big data, what isn't big data, and also data engineering best practices, principles can be applied and should be applied no matter how big your data is. So this is sort of, without being too grandiose, universal truths and all that sort of thing. Also, you'll note that there's quite a few names at the bottom of this presentation. It's just Hakan and myself here today. However, a lot of what we're going to be talking about was information that we incrementally discovered along the way, and tons of people have contributed to this, both at Criteo. These people are all leads in the data reliability engineering team at Criteo, but also outside at conferences like this. So quickly about us. So we work at the data reliability team in Criteo. Criteo, for those who don't know, is a pretty big ad tech company. We have about 2 billion, well 2.5 or something billion dollars in revenue annually. And the scale of things that we do is pretty big. Half a trillion records ingested every day, 20 petabytes of data processed, hundreds of thousands of cores, et cetera, et cetera. We just were talking to one of the leads on the protobuf project at Google, and we told him about our scale. He said, well, you guys might be the biggest company outside of Google using protobuf. So, or the biggest, the heaviest users of protobuf outside of Google. So he's actually really happy about that. So anyway. Also, major difference between us and the rest of the world is we're bare metal. We grew up that way. We have latency constraints for displaying ads. So back in the olden days, the cloud wouldn't give any guarantees about latency, and so that was critical. And then we just sort of learned how to do that. So what are we going to talk about? So first, I'm going to define a few things, so we can all sort of work with a shared understanding. Now, you can disagree with my definitions, that's fine, but for the purposes of my talk, they're important. Then we're going to talk about imperative data pipelines, so sort of the old way of doing things, and then we'll talk about a declarative world, and then talk a little bit about how this works at Criteo. So first of all, what is data engineering? Well, it's fuzzy. I had a different set of slides on this for a different talk where I sort of made fun of all the definitions that are running around on Google. But I've sort of tried to consolidate it down to two things. And that's basically either building the pipelines or building the systems. This is actually important because the same people don't like to do the same two things, actually. I always thought that building pipelines was your gateway drug to wanting to become a systems engineer. But as it turns out, we actually have quite a few people at Criteo who don't care about building systems or tools. They actually just like building those pipelines. And so this distinction, I think, is important. The other thing that I'd like to add to this definition is why we do this. And we do these things to either, I think, extract information out of the system, so observe what happened, and I would consider that classic BI. And we also nowadays do this to inject intelligence into the system, and that would be AI. Now, of course, we can do machine learning stuff and statistics and whatnot in BI, but I would say that the act of injecting intelligence back into the system, feeding that back in through sort of a feedback loop to your online transactional systems, is the AI/deep learning, fancy stuff. I think most people consider this hard. There's conferences about it. And so I think if it's not hard for you, I think it's complicated for everybody. Okay, big data. So again, what is big data, right? Okay, the 3 V's, right? So velocity, variety, volume. I think other companies have extended the number of V's. I have no idea. In any case, it's basically you're dealing with problems that need to be distributed because your data set is so big. That's how I sort of classify it. And sometimes we'll add advanced transformations into that, so the deep learning stuff. But not always, right? A lot of times we're just doing old school stuff in a new environment. Now, why do we have big data? Well, I think, I don't know, Sergey Brin, who said our algorithms aren't better than yours, we just have more data. So I think that just set us all off to the races, right? The more data points we have, the more intelligence we can get out from the system or put back in. And of course, we all know this is hard and complicated. Okay, so what's a data processing pipeline? Well, It's a series of operations on data with a specific order of operations, right? So the previous talks talked about DAGs and whatnot. So obviously there's a DAG involved. Sometimes we can parallelize some of the operations. We can parallelize some of the nodes in the DAG. We can parallelize portions of the DAG. But fundamentally, we're reading a bunch of data, we're doing some transformations, and we're writing a bunch of data out. And I'd like to say that this is also considered hard and complicated, and it's even harder and more complicated in a big data setting. Okay, so TLDR, we could have skipped all that. We're just doing ETL. I think, you know, there's a lot of people who don't like that qualification or classification of what we do, but I think it's useful. First of all, it grounds us, so we stop thinking that we're really fancy people. All we're doing is, you know, plugging A and B into a system to produce C or AB prime or whatever. And then we can compose all this stuff together and make really big ETL systems. Okay, so we have some definitions handled, and so let's talk about what imperative pipelines are. So, avert your eyes, those who don't like Perl. I thought this was, it was fun to write some Perl. It's been a while. So anyway, so I wrote this little script. It works, it's correct. This is a single-threaded way to imperatively transform some input data, right? So basically what are we doing? I won't detail the entire script, but basically we're taking some CSV data and doing some aggregations on it to get the distinct number of clickers. So this is apparently clickstream data, and the number of clicks grouped by hour. Okay. So here's an imperative data workflow that some people who are old enough in this room might recognize this sort of operation. We're going to SCP some data in from our hosts. It's gzip, so we're going to gzcat it, pipe that into our little processing script, and then we're going to probably pipe that into some script that's going to load that into a database, and it creates this little DAG here. Okay. So why is that imperative? Well, because we're telling it specifically what to do, right? And how to do it. So quick analysis. So first of all, it actually has a lot of nice properties, right? It's pretty easy to understand and test. Like anybody can understand that system. It's actually fairly efficient. That ran on my old MacBook Pro at the speed of about 250,000 records per second. So I mean, you know, that's fine. It's modular, right? We can reuse those bits and pieces for different purposes. It's also very Unixy, right? Unix was built around this sort of thing. Unix has worked for a long time, and so if you're a Unix person, that also kind of feels good. Makes you, it's like comfort food for the Unix soul. But on the other hand, it's totally fragile, right? There's some like very, very fragile parsing code in there. We could quickly overrun memory with the way we're doing the aggregations. You know, so it's quite fragile. Error reporting, you know, there's none. You've got standard error if, you know, anything's going to go out that's useful. So yeah, so that's not great. It's also only easy to modify if you wrote it, and that's not just a joke on Perl. Any of these scripts can get that way, right? And it's not going to scale beyond a single machine unless you really, really, really try very, very hard, right? Distributing those algorithms it can be tough, right? That's why MapReduce exists and all that good stuff. So those are the problems. So basically, the distributed problem is the one we're going to talk about because that's principally why we're here, right? We're all past single machine scale. And when there's more than one machine in a system, all this stuff breaks. And so now we need to write complex distributed programs. And the semantics of those things are actually difficult to master. You know, it's all very hard, costly, and it becomes difficult to modify. So declarative data processing. So we're going to use SQL here in our examples. We'll talk a little bit more about some other paradigms as well, but principally we're going to use SQL as the device. So here's that same transformation with a nice little SQL query. It's pretty trivial to read. I won't detail it for you. What do we get when we go to declarative data transformation paradigm? Well, first of all, we get a better distinction between the declaration of what we want to do and the runtime. So now we can compile, we can optimize, we can do all kinds of fancy stuff. We can ensure semantics around how the joins are done, what can be parallelized, what can't be. All this stuff comes, the system gives you all these sorts of guarantees, and you as the person who just needs to transform some data, you don't have to think about any of that. So that increases everybody's productivity and also expands the population of people who can do stuff, right? So it's not just the one expert in the back room who can write that Perl code or whatever, pick your scripting language of choice. And also the compilation phase, especially with a relational algebra like with SQL, can start doing things like reordering things, eliminating steps, can really tackle an optimization problem. So a sidebar, so we're going to talk about SQL here principally, but I did want to address declarative data transformation in other languages. So functional programming allows us to do lazy evaluation of declarative programs as well. And frameworks like Spark, Scalding, and Shio, they allow you to do that, right? The operations like flat map, all the monadic stuff allows you to do very similar things. However, this only describes the pure transformations and the operators that you have access to in those paradigms. And so you can see here that with this is just a cut and pasted code from the Spark example page, and famous word count. And what we can see is that this code is nice. It's very easy to read, it's very understandable, but it's actually fragile. So first of all, we have hard-coded sources and sinks for our data. So that's built into the program. That's not so great. We'd rather inject that into the program. You'll note that we're also talking about how, we're saving it out as a text file. Maybe we don't want to save it in a text file. Maybe we want to save it in Parquet, that sort of thing. And then also, this works by lambdas and in particular closures. And so those closures can encapsulate nasty things that we can't serialize over the pipeline to distribute the program. They can also have nasty side effects that inject non-deterministic operations, and so your pipeline becomes fragile, non-replayable, et cetera, et cetera. Also, you see that the parsing logic is built into this. We're doing a line.split function we're doing a split function on the line, and so that means that we're binding the actual job logic with the way we deserialize the data from disk, which isn't very satisfactory either, because like we all said, maybe the data is going to get big, and maybe we're going to change it to Parquet or whatever, protobuf, whatever you want to do. And when we do that, now we have to go modify all this code and all these jobs. So that's unpleasant as well from a maintenance perspective. Okay, so FP is great. We do lots of functional programming at Criteo. We have lots of Scalding and Spark and all this other stuff in production, but these are some of the limitations of that. So scheduling, so let's switch, okay, assuming you're all still with me and you all agree with all my conceits and all this other stuff, we've all agreed that declarative data transformation is great, and ideally SQL is the right way to express them. So that's cool. But now we have to actually schedule them. And scheduling them is different than running them once, right? When we run them once, we parameterize them ourselves, so we check the inputs and outputs, and we say, oh, that's good, I like it. But now we need to automate that. And so there's frameworks out there, so Apache Airflow was talked about this morning. We have one we call Cuttle, same basic thing, it's written in Scala, but it's effectively the same thing. And actually, I'd argue that what's going on there is actually imperative. I mean, it's lazy, declarative, and all this other stuff, but it is actually, you're specifically telling the scheduler in which way, in what order, and whether those things can be parallelized, the different job units. So that's actually dangerous, because the job is the one that actually needs to know what the data is, what the parameters are, and in many times you're actually expressing those things inside the inside the job itself. And so this is duplicative to inject this kind of dependency declaration. As the data corral speaker said before, the SQL statements can tell you exactly what they depend on. There's from, there's joint, there's all the dependencies are actually directly in the query. And so this is actually dangerous. And this is real-world declarative DAG code. This is in production at Criteo. This is using our scheduler, Cuttle. This is Scalding code. This is orchestrating Scalding code. And I would argue that that's incomprehensible. I don't know. I don't know what that's doing, right? And I challenge anybody to tell me if that's correct, right? It's impossible to determine. There's offsets that are being managed because log A depends on 3 hours of log B, so sliding window stuff, and are the actual job units themselves deterministic? You don't know because you don't know the join matching. You have no idea here. Is this replayable or not? You can't really, the scheduler can't know. You can only hope that those job units have been coded in a way that it's replayable. So this is really unsatisfactory and it's actually unsafe. But it's Criteo code, so it's good. But anyway, and we wrote it. That's our scheduler. So, so let's switch to declarative scheduling. And so SQL exposes basically everything we need. So first of all, we have our dataset dependencies. So you can see that we're binding on raw clicks in the default schema, and we need day and hour, and we're going to parameterize the job by that with those question marks. We can also see that we have a candidate partitioning key in the day-hour concatenation. And then we also have an output schema that we can use, we can recycle for later potential children of this data set. So it's actually really nice, right? The job itself, you write the job and you can actually know what you should do with it to schedule it. Well, almost. So the query by itself actually doesn't tell you about the domain of that partition key. So here, this is time, so everybody can say, oh, well, I know what time is, right? But actually, you're not always going to just be dealing with time partitions. So for example, Criteo has multiple data centers, and we do incremental processing based on the data center that the data comes in from, just as a way to optimize and batch. And so we need to know that as part of the scheduling semantics. So here I've taken days and pets, right? So we need to know this domain of pets. It's an enumeration, and the scheduler needs to know about it because it needs to have a target, right? So here we're missing cat for Tuesday, and so the scheduler's like, oh my God, there's a missing cat, and we need to go deal with that. On the other hand, today's Thursday, and we have like a 24-hour SLA or whatever, so we're fine over here at the tail end. We know that ferret will be computed, it still has time to be computed before we're going to consider it a missed scheduling. And of course it's Thursday, and so we can't possibly compute Thursday yet because we haven't completed Thursday. So okay, so how are we going to do this? Well, we're going to actually extend SQL a tiny bit. So here we can see that we're explicitly stating that for each t in the time series hourly, we're going to create partition of t casted as a date time. So this actually makes the domain of the partition entirely explicit. So I spoke about custom enumerations, so we can actually do that as well. So we can have two variables, and so you can actually sort of look at this as a for comprehension as well for the functional people out there. But we're also expliciting now the another series, which is an ad hoc series, which are our host platforms. So these are groupings of data centers, Asia, EU, and US. And so now we're going to partition by both of those. And the scheduler can now knows exactly what the target is, right? The scheduler can go back and build this. It can build this table once it has that. There's also sometimes things change, right? Especially when we're talking about enumerations, right? So sometimes, so for a period of time, we dabbled with going into China. So that was great, didn't work out, but for about a year we had a data center in China, and so that was an additional platform. And it's really important to have these semantics in your scheduler, because if you just stick with the larger set, China, so you include China, well, your scheduler is going to consistently report there's a bunch of errors because China's not there, right? If you get rid of China, but you still have China data sitting out there, when you do replay, you're going to forget about that. So this versioning is actually pretty important. And we're able to encapsulate that with this sort of extension to SQL. So okay, so that's great. So we've solved the problem. Yoo-hoo, you know, let's all go drink beers tonight. But we do have some trade-offs. So generally speaking, the higher level the abstraction, the more constrained we are in what we can do. That's obviously a good thing and a bad thing. On the good side of things, this means that things can be better understood, safer, that sort of thing. But then we can't always express exactly what we want to do. It can also lead to harder testing because you're probably at a very, 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 very high abstraction level. So you're probably depending on quite a lot of things. And if some of those things, if the abstraction is not very good, MapReduce, and things start breaking underneath the hood, it becomes difficult to trace that and debug it. And not all declarative languages, SQL, lend themselves to code sharing and reuse. So that becomes a little bit of a problem as well. However, the SQL model does address a bunch of these issues. So first of all, the nicest thing about the SQL model is that it comes with a data catalog and schema. And so with that, that allows us to completely remove that from the logic of our jobs. The fact that SQL doesn't allow closures is also great because that means that you can't do stupid things. On the other hand, it does limit code reuse, and it's you can't invent new functionality that's not built into the language. So, but UDFs sort of bridge that gap. But then you can do stupid things in UDFs, of course. But the UDFs allow you to both do potentially unsafe things, but if you pay attention to it, you know you're in an unsafe environment. That's sort of good. And then also you're effectively extending the platform for other people. So this is code sharing as well. Of course, the system guarantees reduce the need to test a lot of things because those are just built in, the guarantees are built in the system, the semantics and all that good stuff. And also that extends to, so the code surface to test, debug, and optimize is reduced. Some people find database tuning complicated and query tuning complicated, but really it just means you have to understand the domain and the system itself, and once you've mastered those two things, then it's actually pretty easy to predict the runtime profile of what you're declaring and change it if needed. Okay, so let's talk about the life cycle of a job in this paradigm. So we're going to talk about, for compactness sake, we're going to talk about the daily clicks life cycle. Earlier it was hourly. So we've got some analyst, and that person is writing, SQL query, this very trivial SQL query, and they've parameterized it to look at the 1st of November and get the output. So one assumes they're playing with this and getting it just right, and now they've gotten it right. And so now they want to schedule it. So they're going to define the domain of the partitioning function. They're going to apply it. They'll bind it to that query. And then they're going to go ahead and push that into a central code repository. We'll have QA bot take a look at it, do some, just make sure the thing actually compiles and do some basic checks. It gets a +1 there. Peer review comes and we get a +2 that somebody else has suggested that query is actually well defined and then and useful. So then it goes out to a staging environment where we can do a full cycle of that query. So we can get an incremental metrics. What's the additional cost of this query into the system? Also it's in a staging environment, so your stakeholder can go take a look at it afterwards to double check that that's what they want. And then the metrics are okay, and so then we're going to push that into production, right? And then now this is producing data into our data catalog that some other analyst can go and start playing with. So now they can actually start thinking about doing the same thing, right? And the cycle repeats. The point here is that the data exploration language becomes the data transformation language, and with a simple extension, we can actually fluidify that entire development cycle in a very, very safe and very, very scalable way. Because thanks to Facebook, Hive exists, Presto exists, and these systems are data center scale compute engines, right? So you can rely on them. Okay, so the declarative data processing dev cycle, just a quick recap of that. So write the query, figure it out, play with it, declare the domain of the partition, commit it to the platform. And then because we're in this purely declarative environment, it's really easy to institute a proper dev cycle for that, including code review and all that good stuff. So I'm going to pass to data processing at Criteo. So we're at the F of Criteo. And so what does this look like at Criteo? So here's our stack. Data flow at the top is this declarative environment. Cuttle is our sort of declarative / imperative runtime for the actual orchestration. This is the thing that exposes the depends on and operators to build DAGs. We have Hive. You see Presto here is in a dashed box. That's because it's a new component. Hawken's going to talk about that in just a couple of minutes. And then, of course, it's all built on top of the Hive Metastore and Yarn HDFS. Okay, so that's a lie because actually we also do non-SQL stuff, as I alluded to with the earlier. So we've tried to do quite a lot to actually bring some of these attributes of the SQL paradigm, so particularly a data catalog, to Spark and Scalding code, and we've done that via a framework. It's called Hippo that allows you to write in either Spark or Scalding, but use the same tests and all that good stuff, and is bound to our catalog system, which is Data Disco, which uses the Metastore. So this is all Scala land. You build your imperative, or your declarative code, but you bind it imperatively, and you operate that yourself. Oh, right, so I forgot. So that's, and then we use Hadoop as our source of truth. So basically everything has to run through HDFS for us to incrementally build new data. Okay, so just some quick, scheduler porn, image porn, whatever. So this is our scheduler Cuttle. It's pretty standard. It's very much like Airflow, but just gives you an idea. So we have a bunch of jobs defined, and some are running, some are waiting based on resources that are available or not. You can take a look at the log output of your job, figure out its status. You can drill into the DAG. We have, so this is our time series scheduler, so it shows you the calendar, so we can see that everything's complete for this workflow, except for the 9th of November, which is a green square, not a green cube, or full filled out square. And so we can dig into that, and we can take a look at the status of all the pipeline, all the jobs for that day and where they are. Also, lineage. So one of the nice things is, so we have post hoc lineage. We actually took the Google Goods paper, and because we do so much SQL everywhere, at every single step of the data production lifecycle, we're able to do post hoc lineage in systems that are outside actually of our system. Because we actually use SQL to express, for example, exports to take data from HDFS and put it into Vertica. We use SQL, of course, to create Tableau workbooks that read data in Vertica, and we can parse all that stuff, and we can build this nice lineage. So for this very, very critical report on the bottom that our CEO looks at every morning, we're able to figure out what the path is for that data reliably. And then also we can have a full understanding of the state of the system because we understand partition domains. And so this is data, for example, in Vertica. So the catalog extends outside of just HDFS, so we can understand the state of adjacent systems. So SQL in production, why do we like it? Well, it's easy to schedule and optimize. It's highly productive. No lie, we have about 1,000 jobs that are managed by 2 ICs. That's, I call that being productive. And that's really big scale, right? So I didn't really mention it, but this is a 100 petabyte Hadoop cluster. It's a petabyte of data in Vertica. So this is reasonable scale. So it's non-trivial data engineering, right? And we've got all that being safely managed by, well, in one section of it, being managed by just 2 ICs. It's also easy to learn. We've onboarded non-engineers onto our system so we can federate work, which is great. So we become less of a bottleneck. And it's getting faster, right? Cost-based optimization is coming. Presto is here. Microsoft Research is doing lots of really interesting stuff about materializing out portions of DAGs inside SQL queries and reusing them. So there's a huge roadmap for optimizing SQL runtimes at the data center scale. So that's encouraging, right? Okay, why it's not universal at Criteo or period. So many teams still use Spark and Scalding due to the ease of testing, right? You can test those lambdas, and that's all, that makes us all feel more confident about our code. It's important. And also you can't get past it. Sometimes you need the expressivity of a full-featured language like Python or Scala. Many teams still also use Spark and Scalding out of pure preference, right? And the perceived shortcomings of SQL. So when they should be using SQL, they're using Spark and Scalding. We're working on both of those points, and our principal work right now is finishing this extension on the SQL stuff that I just showed you, as well as integrating non-SQL transformations into that whole data flow via UDFs and TVFs and things like that, so to be able to include Spark and TensorFlow and all that good stuff in the DAG. Okay, so now I'm going to hand this off to Håkan. He's going to talk about our newest infrastructure component, which is Presto. Håkan.
All right. So given the importance of SQL as a language and declarativeness and all that stuff, we obviously have to look at the different SQL engines, and there's a whole bunch of them. Obviously, there's traditional ones like Oracle, SQL Server, and all that stuff, MySQL, and so we have been using Hive. So we have hundreds of analysts worldwide who are doing ad hoc queries, and Hive is like horrible because we're using MapReduce, and MapReduce is like overkill in terms of doing, writing intermediate results out to disk. So we were looking as a project to, alternative technologies, and obviously we're a little bit late in the game to that. We looked at Impala, Hive LLAP, Dremio, and Spark SQL, but we choose Presto. And Presto is not perfect, but it's getting better and better as we, almost every day. So we tested out these different technologies. We got orders of magnitude better response time than Hive. We got orders of magnitude better resource utilization. There are some minimalistic statements where Hive still makes sense because we're essentially using HDFS as a data lake. So we have a huge number of nodes. So if you do something extremely simple in Hive, where you just sort of create table, a select star from something, Hive doesn't do a whole lot of unnecessary, writing up to disk. And then you have the fact that our Hadoop cluster is so huge compared to the number of compute nodes we have for Presto at this time. So it could be that there's stuff that would actually be faster on Hive, but it's kind of rare. If you do anything non-trivial SQL query on very likely Presto will, if you give it 100 nodes or something like that, Presto will be way faster. So we are in the process of rolling it out. We have a initial cluster with a couple of clusters actually with, we're going to get, we have 100 nodes that we have rolled out already, and we have another couple of hundred nodes coming along, so that's pretty good. We have about 16 physical cores per node and about 256 gigs of main memory per node. So that's essentially our configuration. And that sort of tends to give us pretty good performance. We're not CPU bound really. We are more, so we sort of have this data lake, separation of compute and storage. So our data lake is on HDFS and, on the order of, 100 petabytes or whatnot. So we roll out these compute nodes, a couple of hundred compute nodes for Presto, and the limiting factor probably is to get it sucking the data out of the HDFS, Hadoop data lake. So our primary objective for this is for our analysts to give them better productivity by better ad hoc query performance, and also reducing our cost, because it's more, presumably our hardware costs will go down. We're looking at other use cases other than the ad hoc queries for analysts. We're looking at using Presto for ETL transformations, and our machine learning, we have a fairly large machine learning community, and they're looking into using Presto for part of their sort of pipelines for doing their work. Criteo has its own private infrastructure. We're doing stuff in our own data centers. We're not like doing stuff on AWS or Azure or something like that. So we have to do a lot of stuff ourselves that possibly could be like managed services if we were using public clouds. So I'm going to spend just a minute or two talking a little bit about what it means to implement some technology like Presto in your own data centers. So first of all, so you have the file format issues. So Presto does not quite support all the file formats that are supported by Hive. So we are, as a company, we're moving towards Parquet as a sort of standard as much as possible. And Parquet is generally beneficial. There are some use cases if you have really wide tables with many hundreds of columns where it's maybe not optimal. But for the most part, it's a good standard. There's a lot of companies who are contributing to that, and so we're moving in that direction. But that's has been a little bit of an effort to migrate our data lake to that format. Testing is extremely important. So we try to upgrade our Presto version to the latest and greatest ever so often. We have our own Presto fork where we have some bug fixes and stuff like that. We are trying to contribute back to the community, so we have some Criteo specific no major things yet, but we are trying to contribute back to the standard Presto version, and we have done some stuff along those rows. So we have all kinds of tests running daily. We have a standard test suite. We have canary queries that run ever so often to alert us to whether the system is up and running, and if it's not up and running, we'll get an alert in our Slack channels and all that stuff. And then you have the upgrades, of course. Every time you want to upgrade to a new version, you need to go through a whole bunch of testing, and we invested quite a bit of time in building out the testing infrastructure so we don't screw up when we whatever changes, we can deal with that. Other interesting things when you roll out something like Presto is like, what's the cluster management? It's like, okay, we have like hundreds of nodes. How do you do with that? Do you put them in one big cluster, or do you split them up in smaller clusters and say, hey, you guys get this cluster for this purpose, and another organization gets another cluster for another purpose, and so on. And if you put them all in a big cluster, then you have the resource management, which is non-trivial. It's not Presto specific. You have the same issue anytime you try to squeeze a whole bunch of different applications into a huge cluster. Who gets resources, and what's the priorities and stuff like that. Another issue is how do you prevent rogue queries, because you can have tools that issue really stupid SQL queries, and you can have users who type in SQL and generate really stupid queries that sort of can bring the cluster sort of to its knees. So how do you prevent that? It's a general problem. It's not Presto specific or anything like that. It's a general problem with anything. Okay. So we have monitoring and alerting. So we have Slack channels. We have on-call procedures. You need to do that. You need to have end-user trainings. There's a little bit of take-up if you want to go from, Hive, this SQL dialect difference between Hive and that's pretty much it. So, Justin.
Oh, yeah, okay, so I'll just do the last slide on that. So how fast is it? So this is just Presto's performance. So we see that, so first of all, we see that Presto can return queries in just a couple seconds, even on, reasonable amounts of data, 6 gigabytes of data. It scales well with volume, so the second query takes, pretty much linearly about the same amount of time. It's scanning, on the order of 55 to 60 million rows a second, but about 2 gigabytes a second of data. And we can also see that it's actually, many orders of magnitude faster than Hive in this particular query. 3 seconds versus I think 8 minutes. So that's beneficial. So that's the end of our talk. Thank you very much. One last thing is we're hiring. So we have offices all over the world, and so yeah. Anyway, thanks.
I have a question about the performance, how you were able to achieve that level of performance. Did you do any partitioning for Presto?
Oh, the 3 second runtime?
Yes.
Oh, well, yeah, so that data's partitioned, yeah. I was selecting in that query, it's selected on a specific partition. It's also Parquet, so it does column pruning as well.
Okay.
And so that, yeah.
All right, thanks.
Any other questions? This is great. It's so old school. We're still writing SQL. We write Lisp at my office.
Oh,
so.
wow, that's even...
Any other questions? You got one over here. You can use that mic.
So more about the ETL process.
Yeah.
It sounded like you guys had some Hive, some Spark, and there was another one.
Scalding.
Yeah. It sounded like, based on your presentation, that you guys might have had Spark and Scalding. You're moving away from that into more Hive ETLs. Is the plan to transition everything over, and what has been the performance scalability implications of that?
So it's a great question. We're just in the process right now, so we've basically ourselves identified when we ourselves have built stuff in Scalding, in our case, that should have probably been built in Hive. Mm-hmm. And so we're in the process of actually migrating that right now to Hive. And in the past, we've done, in preparation for this strategic shift, we've done internal benchmarks, and we found that a lot of times Hive is actually faster than Spark or Scalding. Yeah. And we attribute that to basically the heuristic optimizers that are in the Hive versus naive, really naive Spark or Scalding code.
What execution engine are you guys using behind Hive?
Right now we're using just MapReduce. Part of the roadmap is to explore Tez or Spark.
Okay, great. Thank you.